not originally from plasma, from computational dynamics, but today talking about reduced model K-epsilon for cross-field turbulent transport for tokamak plasma. Please.
Yeah, thank you. Thank you. It's a great pleasure for me to be here and to present this work. So thanks the organizer for this opportunity. So this work is a part of a long-term collaboration between IRFM at CA Cadarache and M2P2 in Aix-Marseille University, which is a lab which develops an expertise in computational fluid dynamics. So this work is motivated by we'll say very practical concerns, which are related to the improvement of reliability of numerical solutions for edge plasma simulations, and on the long term, the improvement of predictability of transport code for preparing ITER operation. So I will start first by introducing the general context and the motivations of this work, and then I will I will develop the reduced model that we propose in this context. And I will end my talk by showing you some 1D and 2D results applying this model using the code Solage 3X. So first, before going in the modeling, I will recall you here the topology of tokamak plasma. So to optimize performance in the tokamak, so the plasma is divided in two parts, into regions. There is the first core regions where the fusion reaction are supposed to take place. This is the confined regions where the magnetic field lines are closed and the magnetic surface has a nested surface. And an outer regions, what you can see in brown on the diagram, which is called the scrape-off layer, which is a kind of boundary layer for the plasma. It is a region where the plasma interacts with the wall. And in this boundary layer, the magnetic field lines are open and interact the plasma facing components. Between both regions, there is this red line, which is called the separatrix, which is the last closed field line, so which is really the transition between the confined core and the unconfined scrape-off layer. So by constriction, the magnetic field in the tokamak has two components: the toroidal component, that is Bφ, and the toroidal one, B theta. And there is a strong anisotropy in the magnitude of these two components, the poloidal one being much smaller than the toroidal one. That leads to privileged flow directions along which the numerical equations, mathematical equations, have to be projected simply for numerical facility. So we will define the parallel directions, which is the parallel direction to the magnetic field line, by introducing these two differential operators, which is the parallel gradients, nabla parallel, which is B scalar nabla, and then the perpendicular operator to the magnetic field lines, which is defined by this definition. So now we have the topology of the plasma. When we measure from experiments the diffusive perpendicular transport, so it is here dperp from experiments, measurements show that it is much larger than the value expected by only considering collisions. Okay, and this is the difference between these two estimates is due to turbulence. which is the main driver for this anomalous transport, and to the fact that the value measured in experiments is much larger than the value expected by considering only collisions. So the turbulence is a very important driver for this perpendicular transport. And in the plasma, there is, so due to turbulence, because the tokamak, in fact, is an out of equilibrium thermodynamical system due to strong gradients that are in the tokamak. And then we developed a series of instabilities that cover a large range of spatio-temporal scales. So for the time scales typically evolve from the turbulence characteristics time, so which evolves between the milli and the microsecond, to the confinement time, which is a time of confinement of the energy inside the plasma, which is typically of the order of the second. So you can see that you can have between 4 and to 7 orders on the time scales that you have to consider in the models. It's the same for the spatial ranges. The spatial ranges evolving between the ionic, typically between the ionic Larmor radius, which is of the order of 0.1 millimeter, till the characteristic length, which is here the minor radius of the tokamak, which is of the order of the meter. So we have also, for the spatial range, a large range to discretize in terms of numerics. What we will assume in this work is that the dominant mechanism driving turbulence is what we call the interchange instability, which is a kind of Rayleigh-Bénard instability. Rayleigh-Bénard instability is the instability that occurs when you hit a fluid from below in the gravity field. And you can see here a typical picture, the results of the 2D model obtained by Tokam 2D, showing so the characteristic plumes, typical Rayleigh-Bénard instability, where you have here the hotter, so the less dense quantity of fluid transporting the matter from the x equal 0 to the external radius. And then you can also see in black here some holes corresponding to more dense fluid or colder fluid in the context of convection cells. So the matter is transported from the inner part of the tokamak to the outer part of the tokamak and then to the wall by this Rayleigh-Bénard process. So compared to the Rayleigh-Bénard well-known instability in fluids, the gravity in fluids is replaced here by the curvature of the magnetic field. So due to this instability, in fact, you have some ballooning, because what's the criterion for the plasma being unstable due to interchange instability is the fact that the scalar product between the gradient of the pressure and the gradient of the curvature of the magnetic field must be positive. And so, doing this criterion, according to this criterion, we introduce a strong asymmetry in the poloidal section of the tokamak, as you can see here from this picture taken in the tokamak. So on the low magnetic field side, where you have some filaments occurring here that you see in the picture, which are characterized with the turbulence, whereas on the other side, the plasma seems to keep stable. And it is only because this parameter is only unstable from this side of the machine, while it remains stable on the other side. What we know from linear stability analysis that the linear growth rates of this instability behaves like the square root of the scalar product between gradient B and gradient B. So now, what we want to develop reliable solutions for numerical solvers is mainly because we are interested by the issue of heat exhaust for the ITER operation. So to understand what is the issue, we have just to can just make a simple power balance on what happens, what will happen in the ether. So due to fusion reaction taking place in the core, so we have a fusion power which can be estimated at about 100 megawatts that will be on the alpha particles, so helium-4 particles, and 400 megawatts on neutrals. So the 400 megawatts on neutrals, there is no issue with this power because the power spreading as the neutral particles do not see the magnetic field lines. So the power is spread over the whole surface of the tokamak, which is about 500 meters square. So when you calculate and you estimate the heat fluxes on the surface, so it's okay, there is no issue on the value with respect to technological constraints. However, regarding now the outer power due to alpha particles, so the 100 megawatts, you have to add to this power 50 megawatts due to heating, which are injected in the plasma to heat the plasma and produce fusion reactions. And we can estimate that can withdraw about 30 megawatts due to radiations by impurities in the tokamak. So at the end, you have a budget of 120 megawatts to exhaust from the tokamak, but on contrary to neutral particles, this power is brought on charged particles, and when they will follow the magnetic field lines, and then they will be evacuated here by the channel, by the scrape-off layer that I introduced in my first slides. So which is a very narrow boundary layer at the outer part of the tokamak. And so, as the estimate of this scrape-off layer is the order of the millimeter, you can see that the spreading surface on which this 120 megawatt must be spreaded is only of between 1 and 2 meters square. So doing that, you arrive at an estimate of the fluxes, of heat fluxes, which is around between 50 and 60 megawatts per meter square, which is very far past techno limits. So how do you estimate the thickness of this scrape-off layer? You can get that just by assuming the balance between the perpendicular transport to the magnetic field lines and the parallel one. So if you do that, you write the balance between the pulse time in the perpendicular directions with respect to the time in the parallel directions. And so you get this estimate, a lambda q, which is the thickness of the scrape-off layer, divided by your diffusive coefficients, which measures the amplitude of the perpendicular transport. So square of that is the perpendicular time. And you compare this time to the parallel time, which is given by L parallel, which is the parallel convection length. So typically 2 pi multiplied by the safety factor Q and the major radius of the tokamak. So it's of the order of 100 meters divided by the sound speed. And then you get an estimate here of this lambda Q. Why it is important to have an estimate of this lambda Q? Because when you write now, as explained, the flux, the heat flux that will impact the wall, you get this formula. So it's the power that you have here at the output divided by here the effective surface where the spreading will take place. And so the lambda Q is really a critical factor because all the other ones are not cannot be changed. The power is the power due to fusion reactions, and these parameters R0 and F here, which is are given by magnetic geometry and then cannot be easily changed in the tokamak. So the real parameter what you can play is this scrape-off layer thickness. So due to these estimations, safe operations for ITER requires absolutely to reduce So this power density at the divertor targets, which is far from the technological limits. So to do that, we need to design what plasma physicists call optimized scenario by playing on the magnetic geometry, by changing the shape of the magnetic equilibrium. You have a kind of super X, snowflake geometry, or you can play also on the position of the X point and so on. You can play also on the operation condition by getting detached regimes to try to reduce the impact of the heat fluxes on the targets. And you can also use impurities, inject impurities or impurities related to the plasma wall interactions to cool the plasma by radiations and collisional loss. But the difficulty here is to find the optimum between reducing the fluxes at the targets and keeping optimal condition in the core, so hot, not region in the core to favor fusion reactions. So to help in the design of such optimal scenarios, there is a need of efficient numerical tools. Efficient means that we want reliable solutions, and we want these reliable solutions over a short reach of time to ensure engineering and operation uses. So there is really a concern of practical applications of, I would say, engineering concept. So if we look now the landscape of existing numerical models developed in the community, the plasma communities, so you have a large set of codes and models to simulate plasma. So on the left here, where the time, the computational time is the highest, but the model in terms of fidelity is the highest too, is the codes based on the big methods, particle in cell methods, where we calculate the trajectory of each particles on time and in the tokamak. But as you imagine, the number of degree of freedom is very huge, 10 to the 12 at least, and so the computational cost is very huge, and the return time for solution is quite long. So this kind of approach is only, at least for the moment, related to fundamental investigations in simplified geometry. After that, you can consider using statistics. You can not solve all the trajectories of particles, but you can solve the distribution, the probability distribution functions, and it's a domain of kinetic and gyrokinetic codes. So in the phase space, so it's codes that solve equations in 6D or 5D when you use a reduction related to the gyrokinetic model. But as you see, the number of degree of freedom remains also very huge. And if you want to consider also the complexity related to the geometry, because as you have seen on my first slides, the geometry is relatively complex in the tokamak cross sections. So this kind of codes still remain in the domain of related to fundamental research and applications. So then, if you don't consider these two kinds of applications, which are too expensive, you come back to what we call the fluid models. So the fluid models are obtained by taking the successive moments of the PDF of few plus of equations, and then you can derive from these codes 3D models or even 2D models. And so you obtain, doing that, a strong reduction in the modeling, a strong reduction in the number of degree of freedom, where you are starting here to 10 to the 12, and you arrive here to 10 to the 5, about 10 to the 5, so you have a reduce of about 7 orders in the resolutions. So that would be this kind of codes which will motivate our research. So the idea of this work is to improve the predictability of such codes obtained by model reduction from more finer approach. Okay, so now we are in the frame of fluid models. So there are 3D and 2D models. So we are concerned here by, at least at the beginning, by 2D models. So how to go from turbulence models, so the 3D models, to transport codes. The idea is to use time separation, so coarse-graining operation that was discussed in the previous talk, is to separate any quantity that you have to solve in the model by an average quantity, which is average of toroidal direction and on time, and to consider fluctuations, two parts of the fluctuations. So F second here, which is fluctuation due to low frequency in the motions that will be resolved in the model, and F prime, which corresponds to the highest frequency, what are very expensive to resolve, and that will be modeled in the code. So doing that, averaging the 3D models by considering this decomposition, you obtain a strong reductions in the number of degrees of freedom, and so in the numerical cost of the simulations. However, when you average using this procedure, when you average your fluid equations, due to the nonlinearities in the equations, you need to close your new model, because the transverse turbulent fluxes is a new unknown in the problem for which you don't have equations. And so this is the main issue for transport codes. Alors in CFD, we have the same thing. That's what we call the Reynolds average Navier-Stokes. So in CFD, typically we solve equations. The flow are governed by Navier-Stokes equations. And for engineering applications, when we have the same issue, is to reduce the cost of numerical simulations. We need to reduce the cost, and to reduce the cost, we consider only the equations at the statistical level by taking the average, as I did, of the Navier-Stokes equations. And so what is done in CFD? In CFD, in fact, we used what we call the Newton analogy. So the Newton model, which is here, which is the model for the stress tensor in fluids that can be expressed as a static pressure and the rate of strain here. So the idea is to say that for the transverse turbulent flux, we can model this flux by relating it to the mean velocity gradient, as we did for Newtonian fluid for the stress tensor. And the idea here is very simple, that the propension to generate vortices should be proportional to the mean velocity gradients. So this is the idea, which is the end, is what we call the gradient transport model. So in plasma, so it's what it did actually in the current version of transport codes. The transverse fluxes are assumed to be driven by local velocity gradients. And so when you do that, then you need, if you assume that is true, you need to introduce a proportional factor between these two, and this is homogeneous to a diffusion coefficient. It is a major change in the simulations because you go from microscale convective motion to macroscale diffusive transport. So there is a change in the way that you consider your turbulent transport in the model, but this is a price to pay, I would say, to reduce your cost in the simulations. Alors, the example that we have for plasma, so is this one. And for example, if you consider the plasma density, the fluid model, so we have here the convective transport of density fluctuations by the drift, the velocity drift. So it's average quantity, so it's until the v tilde, so the fluctuations of the density multiplied by the fluctuations of the drift velocity, and I take the average on the toroidal direction and on time in the same process that I introduced before. And then I close these fluxes by saying that it is equal to the mean density gradients here, and brackets. And there is a proportional factor, which is an effective diffusion, which is different to the molecular one. It's a new node of the problem. And the difference with the molecular one, so the molecular diffusion is related to the property of the fluid, and the effective diffusion is no longer related to the property of the fluid, but is related to the property of the flow. Okay? And then you have now, if you do this process, we have now to solve a new set of 2D equations with new unknowns, which are these perpendicular transport coefficients. And so this is the motivation of our work. It's how to express, how to estimate as accurately as possible this diffusion coefficient. So if you, just to show you here what's typical, what is a typical model that we solve in the transport code. So there are plenty of models, but this is one. So typically we have conservation equations for fluid quantities. So under many assumptions that can vary between different models and so on. But anyway, generally there are two drift reduced conservation equations. You get conservation equation for the plasma density, the parallel momentum, the ion temperature, the electron temperature, and an assumption on the parallel electric field. What I would like just to show you here is that typical equations are in two parts. There is a part in the parallel direction to the flow, as I introduced in the first slide, which is related to the property of like a compressible fluid in CFD. So with a compressible process with a very fast speed in the parallel direction along magnetic field lines. And you have a perpendicular motion, which is assumed to be diffusive because due to turbulence, as I discussed before. So in the model, we have a series of coefficients, which are effective coefficients, like the diffusion for the density here. But you have also the viscosity here for the momentum and the conductivity for the temperature. So all these coefficients must be provided before starting the simulations. And as you assume, the reliability and the quality of your solution with respect to the physics at play, which depend on the value that you will impose and you will fix to these parameters. So what happens in current codes? In current models that has been used to design ITER or that used in different institutes. So these coefficients are assumed to be constant. And they take typical value in the range 0.1, 1 meter square per second. So this is values that you imposed. So these values is supposed to be relevant with the turbulent transport that you have at play in the experiments. And it also related to numerical constraints because reducing the value of these coefficients leads to increasing the number of degree of freedom that you have to impose in your simulations because you increase the turbulence intensity in the model when you reduce the value of the coefficients. So typically in simulation, you choose a value, for example, 0.1, and you run your simulation with this constant value, 0.1, in the domain. So this, you can do a bit better than fixing the value. You can take an estimate from experimental profile. So you can get the experimental density profile at the Loffisal midplane, the radial profile, and taking the gradients on this profile and the particle flux, you can have an estimate of these coefficients, and you can do a kind of feedback loop, for example, when you force your code to match the value obtained in experiments, at least at this one location, and run the simulation. So you make a feedback loop control on the value of D, matching the experimental value at the physical plane, and the codes make its own estimate of this coefficient at the other locations in the plasma. But you see that the predictive capability with such kind of approach is very low, because you need to have first the experiment to have an estimate and to force the value of this estimate at one point. But we are unable to predict what will be in the next experiment on another machine, what will be the value of these coefficients. I would like now to come back to how important it is to have a good estimate of these coefficients. So I already showed you the beginning that it is a parameter which takes place in the estimate of the boundary layer thickness at the outer part of the tokamak, on which is based the estimate of the heat fluxes at the target. So you see that if you have a wrong value of this parameter here, or the wrong distribution of this parameter in the poloidal cross-section, you will have a wrong estimate of the boundary layer thickness, so a wrong estimate of the heat flux at the target, which is one of our concern for the heat exhaust. Second point. So this parameter, as I showed you, so it's used to close the transverse turbulent fluxes. So it is a measure of the transverse turbulent flux magnitude. What we show here, it's simulations obtained with higher fidelity fluid model, so 3D model, where we have estimated the repartition of the total turbulent flux, so the total E cross B flux, which is the total drift, the total flux due to the drift velocity induced by E cross B. And so we decompose this flux in two parts, a mean field part and a turbulent part. And what you can see here, so here it's typical the distribution of these two components, with three parts of the three quantities, the total, the mean, and the turbulent flux. And this is a distribution along magnetic surface around the separatrix. And what you can see is that in a large part of the domain, the total flux, the largest part in the total flux is given by the turbulent flux. So you see that if you want to estimate accurately the total flux, perpendicular flux simulations, you have to have a very good estimate of this turbulent flux, and not only on the mean field flux, which will be given by your coarse graining procedure in the transport code. So it's very important to have a good estimate of this magnitude of this part of the fluxes. Other things that we have, that I showed you at the beginning of my talk, is the ballooning of the transport due to the interchange mechanism. As I told you, the interchange mechanism is related to the scalar product between the magnetic curvature and the pressure gradient. And a very simple analysis shows that only one part of the poloidal section is unstable to this instability. The other part, the scalar product being negative, it remains stable to the interchange instability. So the consequence of that on the transport is that you have a strong ballooning in the poloidal cross-section. And so it's not an homogeneous distribution of the turbulent fluxes over the whole sections. So now if you come back to D, to my parameter D, so if you take a constant value of this parameter, that you will have a constant distribution of the turbulent transport over the whole surface, over the whole poloidal surface, that is expected to be wrong, as you have seen from experimental visualization, and as you see here from numerical simulations. So two things. So it's important to have a good estimate of D, because the turbulent flux is dominant in the total flux. And then you have also to integrate that the fact that this transport flux is ballooned in the poloidal cross-section.
Need not protest the day. have to calculate D as part of the solution to the problem?
You mean to have an estimate of D after the simulation?
D, you have to calculate it, right? From the ultimately from the fluxes that drive the system.
Yes.
And the second question is, what makes you think you have any D at all? Because in H mode, I mean, the whole point of the Goldstone boundary layer business is you have a collapse of the turbulent diffusion, and you're left with only a neoclassical boundary layer. And I haven't heard a word about that very important issue so far.
No, it's true. You're right. It's absolutely an important issue, but I will say this is limitations related to different models.
But I mean, how, in a sense, the essence of the problem is how you overcome the collapse of the turbulent boundary layer. And by the way, the other issue is, of course, is that it's not a kind of smooth turbulent boundary layer, even when you have it. It's highly intermittent, which is, of course, the blobs business.
Yeah. I agree absolutely on all these points. But I argue that the motivation of this work is to work in the free models approach, in which we assume that the turbulent flux is purely diffusive. And so our motivation was how to improve the modeling of these diffusion coefficients. But for sure, we are far from many physical conditions in which the model is I would say, is wrong.
Show how to compute this coefficient, but it is for the moment for example, and we have ideas for how to improve.
Presumably, you're interested in a plasma that ignites. At which point you're going to be in H mode.
Yeah. But I have a point. Pat, on that. Yeah, showing how the model is able to, at least in 1D, to predict transition to H mode.
But it's true, as you will see, this is a way to have an estimation of radial transport in element, but we have already ideas following your paper to put a relationship between the coefficient and the shear flow at the ultimate plane in order to try to get the transition and to take into account the variation of the coefficient depending on the shear flow.
That's the essence of the problem.
Yeah. I agree. Just what we're working in the framework. This framework is the 2D fluid models, and in this kind of models, the turbulent flux is assumed to be diffusive. So there are strong limitations in this assumption. It's for the moment we don't have better models in this kind of this framework, and this is the purpose of this work, is how to improve the estimate of this diffusion coefficient. And you will see we'll show you some 1D results where we are able with reduced model to obtain the transition with the formation of barrier transport playing on the estimate of this. Okay, so about as I told you, the idea is the same than in CFD, is to have numerical tools able to provide some global quantities relatively accurate, as we did, for example, in aerodynamics, when you resolve Franz Navier-Stokes equation, where you're interested by simulating the flow around an airplane, like this one. But for an industrial, it's very important to have a short return time on the simulations. And you use the Franz approach. You use a coarse graining approach when you average Navier-Stokes equation, and you get average field, as you can see here. This kind of approach has strong limitations, as Pat mentioned, also in CFD. But anyway, it provides, at least for global, for example, aerodynamics properties, but you are an engineer, you want to know, to estimate the drag, or, for example, if you we are playing, but you can get many flow conditions, not in all flow conditions. For example, if you have separation, boundary layer separation, or strong unsteadiness in your flow, the simulation will be wrong. But at least in most of the configuration, you can have a good estimate of the turbulence quantity. And you compare here the solution that you get with this kind of approach, so coarse graining approach, and here the same results, but obtained with a higher fidelity model, when you resolve a larger part, as you've seen here, a larger part of the spectrum. So you're resolving here more scales in the flow, so you have more details. It is much more accurate, but it's much more expensive. So it's another kind of does not answer to the same conditions. And so it's typically what we want to do for plasma. Say if you make the comparison, so here you will have the results obtained by the 2D transport codes, where the equation has been averaged. So you have only global estimate of the coefficient transport compared to 3D solutions obtained with where you resolve more scales in the flows and strong unsteadiness. And you see here the repetition of the density fluctuations with respect to the output given by the 2D code. So we are working in this framework, and for sure there are many assumptions that are wrong and that are not true in all situations, but it is the framework of this study. So now what we have done to improve the situation. So first, I will call here some well-known results obtained in Kolmogorov theory. So it's also a very simple theory, but it's the only theory that we have to quantify exactly for turbulence processes. It's the theory for isotropic homogeneous turbulence. And what you see in this picture of the turbulence, again, very simple picture of the turbulence, that is that you have two key quantities. You have the turbulent kinetic energy per unit mass here, which is defined in the talk by kappa, and its dissipation rate, which is the rate at which the energy is transferred from large scale to smaller scales in the Kolmogorov vision of the turbulence. So in the spectrum, in the vision of Kolmogorov theory, so you have a large scale containing energies. You have an inertial subrange here, where you can get that the only variables which is for the energy spectrum here is the dissipation rate. So K here is not kappa, it's K, it's the wave number. So you have a relation between the energy spectrum and the dissipation rate, but you can transfer in between kappa, so the turbulent kinetic energy, and the dissipation rate that will be used later in my talk. So the idea is that when you have two key quantities, so kappa and epsilon, and so what we are doing in CFD, in the RANS model, what you call the K-epsilon model, which is very popular in CFD, is to say, okay, that this diffusion coefficient here, I will express it as C, the constant, multiplied by K square over epsilon. Okay. So what is interesting with that you allow, so by considering this expression, the time and space nonlinear variations of the coefficient, because now the coefficient will vary with kappa and epsilon. That allows to analyze transients, and you will get an estimate of D at each point and at each time step in the simulation by assuming that. Because it's purely based on the dimensional analysis. Okay, so it's C typically the application is equal to 1. Okay, but it could be different. What? It's equal to 1? No. No. There is no demonstration. It's just the use. No, there is no demonstration. This relation is simply obtained by a dimensional analysis, okay? And so we should say that there is a proportional factor between the two quantities. The fact that what? Yeah, it's a definition. You assume this definition. We say, okay, the D, following a dimensional analysis, can be right. Kappa square over epsilon. It's another issue. We can prove that from highest fidelity model. In some situations, it works well. We can show for example, if you take 3D models, you will resolve the spectrum with no assumption on the diffusion coefficients. You can show that in some flow configurations, this relation is true. But there is no mathematical demonstration that is the universal relation.
There is a result by GI Taylor, which shows that actually the diffusion coefficient don't really depend on the form of the inertial one. It's already related to what's happening at zero frequency.
Yeah. Yeah. And so?
We does not depend on the inertial range.
No, it's the assumption that we do. We are doing. We have no over. You have the choice between imposing a constant value of D or relating or trying to relate D to over flow quantities which are related to turbulence. So in Rand's model, so it's just a starting point. I would say kappa and epsilon, you can choose over quantities. There is a group in Belgium working on entropy and over quantity. You can make the choice. The idea is to say, as it's done in CFD, how to express D in terms of over quantities to have an estimate of this diffusion. I agree that it is. The vision is very simple. It's based on the Kolmogorov theory, and for sure, the Kolmogorov theory does not work for plasma turbulence. But even for many configurations in CFD, it does not work, and a lot of people use it because the results are good. Yeah, no, I understand. Yeah, yeah, I understand. Yeah.
So the diffusion coefficient D and what time and space means you calculate kappa epsilon every time into this.
Yeah, I will show you now, because now we need to design a model to calculate kappa and epsilon. Okay, it's my next slides. So in this context, so many discussions on assumptions and the validity of the model. I agree with all these concerns. But anyway, it's we are convinced that it is an improvement with respect to what exists now in the transport codes. So you have your two quantities, kappa and epsilon, and now we need to estimate these two quantities. Here you have two possibilities. We have a possibility which is used in CFD is to derive an exact equation for the turbulent kinetic energy from the Navier-Stokes equations. You make your Reynolds decomposition and you can have an exact equation for K. The equation of epsilon is a bit more tricky to obtain, and you have some closures to implement in the equation. But anyway, you can derive relatively in the frame of Navier-Stokes equation relatively accurate transport equation for kappa and epsilon. So here the choice has been different because the situation is more complex than in fluids, and the equations are too complex to obtain exact equations for kappa and epsilon. So what we did is to say, okay, we are going to design algebraically a system of equations for kappa and epsilon on a very simple physical consideration. So it's a very general transport model where you have a transport of the total flux for kappa and epsilon, so the divergence of K for kappa and the divergence of capital E for epsilon. And on the right-hand side, you are assumed to have a source terms, which will model the local evolutions of these two quantities, kappa and epsilon. So the divergence on the left-hand side of the equation accounts for the transports of these two quantities. The source terms will account for local properties of these two quantities. And we have added here terms minus epsilon in the equation of K to have an explicit coupling between the production of turbulent kinetic energy and dissipation rate. And this term will allow to a damping of K governed by another equations, which is the equation on epsilon. Okay, and so you have like that. You introduce in the model a degree of freedom, for example, with different time scales for epsilon and kappa. Yeah.
Keep in mind between 50.
Okay. 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 So now, what we have to do is to design the source term. So the source term we have considered a generic form of this source term with a linear drive term, which is parametered by gamma, kappa, and gamma epsilon, so with the same kind of terms for kappa and epsilon, and the quadratic saturation terms, simply by simplicity, the first nonlinear terms to saturate and to be sure that the value of kappa and epsilon will be bounded. So we have gamma kappa and gamma epsilon, which are growth rates, and you have quadratic saturation terms to bound the system. The term, the nonlinear term on kappa square here is just used to be sure to have a damping on kappa, even if epsilon equals 0. Because here, as we will discuss later, we have two processes of dissipation. You have the process by the nonlinearity kappa square and the dissipation by epsilon. So now we have to determine all these quantities. And to do that, I will consider the local evolution of the system by, for the moment, not considering the transport term, but only the local system. So I ignore the coupling between the two positions in space. And then I consider this new system, which is a kind of predator-prey model now, well known in plasma physics. So where epsilon plays the role of a predator and kappa plays the role of the prey. So it's very popular in plasma and with the large work of Pat on this in this domain. And yeah, the idea that the way that the domain is designed, so the epsilon for the moment, because we'll see that in the beta epsilon we have an introduction of the kappa, but for the moment, as it is written here, you have the predator evolves independently of the prey, and we have two fixed points in the for the predator. At this stage, so first we have to design the linear terms. So the linear terms, what we will consider is that they are equal for kappa and epsilon and equal to the growth rate of the interchange instability, which is the main mechanism that we are assumed to be to play a role in the turbulence production in this context. And then you have an analytical, you can consider an analytical expression of this growth rate, which is based here on the pressure gradients of the ion pressure gradients. Capital R is the major radius of tokamak, and CS is the sound speed, and BT is the toroidal component of the magnetic field. So typically, when you introduce this value as a growth rate in your predator-prey model, there's the implicit rule that the real parts of this quantity will be 0 if the produced scalar is negative. And you produce simply by that the expected ballooning of the local drive, because the growth rate, you will have a production of kappa and epsilon only in the part where the toroidal cross-section, only in the part where the interchange stability is unstable. So now we need to design the quadratic saturation term. Alors, to do that, first the terms on epsilon, so the beta epsilon, how to fix the beta epsilon. So we will use the self-similarity turbulence hypothesis proposed in Kolmogorov, as I told you, that allow to relate the dissipation to the turbulent kinetic energy by this relation. And then we will assume this relation between epsilon and kappa that allows us to fix this parameter as a function of kappa power -3/2, and with multiplied by a function here, which is homogeneous to a velocity in terms of dimension. So if you consider here this velocity, but what we choose the typical velocity, the typical characteristic velocity given for microturbulence in the cross-field transports. which is given by the rho star CS. So rho star is the dimensionless Larmor radius for the minus minor radius of the tokamak. Alors, how to get an estimate of this V? But we have just to consider, so we use the expression of lambda sol obtained by the equilibrium between parallel transports, perpendicular transports. So the estimate that I already provided you. Here you can get from the scaling laws. So scaling laws obtained in different machines, in different tokamaks. They observe that the lambda, the boundary layer thickness behaves like a constant multiplied by the safety factor and the Larmor radius rho star. And so you take the opportunity here to introduce this estimate of lambda sol in our model to hope get the right estimate of the lambda sol when the code will run. And then if you assume that again that the diffusion coefficient is equal to this V square over the growth rate, so the inverse of time, you have an estimate here of this, what could be this velocity in the model.
Gamma is the
yeah. No, gamma here is the growth rate, so it's the inverse of time.
Yeah, but before you were saying that.
It's the same, it's a gamma, it's the growth rate of the interchange stability here.
Okay, but before you were saying that actually K squared divided by epsilon.
Yes.
So epsilon.
No, but here. Yeah, so yeah. Remark, just to show you that it's a choice that we did to relate epsilon to kappa using the Kolmogorov theory, but you could use another relation. Epsilon, you could assume that epsilon behaves like kappa power to eta here. And we have shown, so maybe I go through this part, you have shown that whatever the value of eta, this is a solution here that we get on the system, whatever the value of eta, for eta larger than 1, as the quadratic term plays its role, and kappa and epsilon asymptotically converge to 0 for large value of the control parameters. So it's what we expect from this value. So I will say that we have taken eta equal 3/2 in the program. In fluids, they use eta equal to 1. But whatever the value of eta, you see that it does not impact too much the behavior of the solution. Finally, there remains the term beta kappa, so the saturation term on the turbulent kinetic energy. So we consider here a dimensional analysis to see that this parameter is homogeneous to diffusion coefficients, and to provide connections to published predator-prey models developed by Pat. They will decompose these diffusion coefficients in 2 terms, which is the value kappa omega, which is the characteristic value of the turbulent kinetic energy, divided by the spectral waves delta omega in terms of frequency of the turbulent kinetic energy. We have shown that what we want to keep in the spirit of the model, and we want that this parameter is large to keep the saturation process governed by epsilon and not only by the quadratic terms introduced in the equations. So we can show, we have shown in the recent paper that this value will correspond to a weak turbulence regime. So we need to consider only large value of this. So this is what I propose here. So you can simply show by considering the steady state of your predator-prey model, you can get a second order equation on d, dv, and d omega. And when you consider the solution of the model here, of these 2 second order polynomials, you have 2 kinds of regimes that you can get from this solution, assuming that the coefficient d omega that we want to design is large with respect to dv, or this is the opposite, d omega is small with respect to the dv. So the choice it's made in the current version of the model is to assume that d omega must be large with respect to dv, to keep in the weak turbulent regimes where we know that the diffusion coefficient behaves like d square. It is what it is expected from quasi-linear theory and what we want to do for plasma application. So in typical simulations, so d will be considered as large with respect to 1. So at the end, we arrive to the final model. So the full model. So now we have designed the constant and the local evolution of the model, considering a predator-prey model. And now we put all together. So we have the transport, the diffusive transport in the perpendicular direction, and the convective transport in the parallel direction. So in the spirit of conservation equations that we have for work quantities in the plasma. We need now to design the ratio between all these parameters. So to do that, we come back to experimental measurements, experimental estimate of this ratio. And so that leads to considering equivalent to turbulent mid number equal to 1, means that the mu will be equal to D, will be equal to kappa square over epsilon. And for the conductivity, so the thermal, the electron thermal and ion thermal conductivity, which we assume to be equal, we have a factor 2. So that corresponds to a turbulent point number equal to 1/2. Okay, so first, come back to the 1D model first to show how the model works. So this is the reduction of the 2D equations to 1D. So we are integrating the equation on the radial direction. So integrating in the toroidal direction. So field equations, vorticity equation derived from the charge balance. We added some neutral diffusive equations showing to replace the role of particle source in the model, and then our kappa epsilon model here. Source terms are designed to correspond to what we expect from the physics, with a recycling source here picked at the separatrix. So this is a typical profile for neutrals. And what we have to keep in mind is that we, in the strategy, in the computations, we design the source to keep the constant value of the density as a separatrix, which can be understood as a particle injection rate with feedback on the separatrix, which is quite classical in transport simulations. So what happens now? So you simulate your 1D model, and you make a scan on the input power in the model. And so we have no more constant parameter to impose, only C, the proportionality constant between, which is equal to 1 here. But what you observe is that the 1D solution shows the expected behavior. It means that you have, when you increase the power injected in the system, you have an increase of the boundary layer thickness that corresponds to an increase of the diffusion coefficient and decrease of the gradient of density. Everything is coherent. And since the value of density is kept constant at the separatrix, that corresponds to a decrease of the density in the core. So it's what you see here. When you increase the power, so the density value decrease in the core, and you have here gradients become flatter around the separatrix. So again, when you increase P in, you have, as expected, an increase of the temperature in the core and the separatrix, because you simply increase the energy source in the model. And we get the model leads to a power law variation of the temperature with respect to the injected power. So you can see here, both in the core and the separatrix with two different components. And as you have an increase of T and a decrease of N, globally you have the model provide an increase of the pressure T0, which is provided here, with respect to the injected power and the core. So I think it seems to be coherent. So now, if we look at the evolution of Dn, so the diffusion increase also as a power law of the power injected in the simulations, and then, as expected, you get an increase of the gradient length, which is coherent. Notice here with the closure that we have imposed in the model, since we have assumed that the velocity scale as a rho star CS. So it means that the gradient length, we say that the square root of the temperature is more or less So it's the temperature, as we have shown on the previous slide, evolves like this power of the paying. And so the estimate, the variation of the gradient length is coherent with this estimate. So everything is fine. Now, have a look on the scaling law. So this is the scaling law provided for ITER. So the variation of the confinement time with respect to different plasma parameters like the plasma current, the toroidal component of the field, the injected power, the geometry parameter, and so on. And then you have this, this kind of variation to measure on different types of machine. And so what the model provides, you can see that with the simple model, you get a relatively good estimate of the variation of the confinement time with respect to the injected power. And also, so this is the two profile here in red. And also when you vary the intensity of the toroidal component of the magnetic field. So last point to connect to the question of Pat at the beginning, we have tried to, because in this very simple vision of the model, the dissipation only acts when you transfer at smaller scales. But we know that in plasma, there is also an important role playing by large-scale flow in the dissipation process due to chairing of the eddies by typically the zonal flow. So there is a large corpus of work here, theoretical work showing the role of that. So a way to take into account such effect in the model would be to add a second predator of paper, typically related to these zonal flows. But what we have preferred to do in the first step in the development of the model is to modulate the velocity V by taking into account some shearing in the model by introducing a dimensionless parameter, omega tau square, where omega is the radial shear of the zonal flow, that will be assimilated to the zonal flow, but will be estimated by here from the radial profile of the electric potential. And tau will be a free parameter, which is a time to enforce with the time that we want to enforce this sharing. So it will govern the sensitivity to the sharing of the solution. So we modify. So you previously in the previous version, so the model was V equal rho star CS, and now we add this term to take into account this sharing with a free parameter minus R, which governs the amplitude of the transition from the low to the high shear limits to have a good control on the shearing. So if you see at high shearing, so when this parameter goes to infinite, that you have a V what behaves like rho star CS 1 over R. And when and so since D is assumed to vary like V squared over gamma, so if you want a reduction of 2 on D, and so in the step of layer, you have to impose R equals square root of 2. So it's first guessed to run the model. So if you do that, what happens? We have the model is able to simulate the transition between no shear regime to the strong shear regime when increasing the injected power. So here it's a profile of Ti versus the normalized radius when you increase the injected power. Okay. And what you see that varies progressively by increasing the power, steepening of the temperature gradient in the vicinity of the separatrix here, with two regimes clearly. Here, a low energy regime and a high energy regime, where the gradient takes shape at the separatrix. And here we have plotted the value of the diffusion coefficients, the evolution of diffusion coefficient with pay-in at different radial positions. And so you see that what we are close to the separatrix, so around the 1, these 3 values in blue, and you see that after Pi equal to 2 over 2.5, then you have a strong decrease of the turbulent transport. The turbulent transport being even equal to 0 when the injected power is very large. So in fact, we have a kind of nonlinear feedback process Well, you have first a driving mechanism driving the shear layer, which is related to the electric potential, which behave in the model that we have, like Ti over here in the core and T over here in the soil due to parallel loss. So here you introduce initially in the model shearing on this electric potential, but when you increase the injected power, so you increase this shearing due to the electric potential, then you increase the shear velocity that is estimated from this radial profile phi, and then you increase the weight of the shear terms in the expression of V. You modify the diffusion coefficient, you increase the gradient, then you modify your kappa epsilon transport, and then so if you modify your turbulent transport, you modify again the profile of phi, and you have like a nonlinear feedback process able to predict some kind of transition to a transport barrier. Finally, I will end just by showing you first the 2D results where we have compared numerical simulations to an experimental discharge on the Tokamak West in Cadarache. So we have run Solage 2D coupled with the neutrals code IRINI, in which we have implemented the kappa epsilon model extended to 2D. So this is the result that we got. So first, as expected by constriction, we have here we have the variation of kappa over kappa max on left, and here the variation of the diffusion coefficient. We measure the turbulent transport in the model. As you see, we have a good prediction of the ballooning transport in the sense that the turbulent transport is only localized on the low field side of the toroidal machine. And then you have some spreading of kappa and D because they are transported also in the parallel direction. So you have some extension of these unstable regions to other part of the tokamaks simply by spreading the convective transport of kappa and D. So this is something that you can compare to simulations obtained with higher fidelity models. So the agreement is relatively good. So again, there is no parameter to fix, only one constant to provide in the model. Now, if we look at some more quantitative comparisons at the outer mid-plane, so we compare the electronic temperature and the electron density at the mid-plane. So we have here variation with the radius of these two profiles. And what you can see is that in the simulations, there is no strong variations between the divertor and the mid-plane. So that seems to correspond to what we call the shift-limited regimes, which is not observed in the experiment. So I just show you that to explain the difference that we get later in the profile. So probably the simulations are not run in the good regimes, since there is no too large difference between the divertor profile and the mid-plane profile. However, if you compare the profile obtained between experimental measurements and numerical profiles, so you can see that there is a relatively good agreement, even good agreements in the near soil regions, and the situation is not so good in the far soil, where you have probably too strong numerical gradients. So what we have to understand why we get this behavior of the solutions. And so finally, at the divertor profile, so we have scaled both profiles to match in the same picture. So you can see first that there is an overall agreement between experimental profiles and numerical ones obtained from 2D simulation. So the shape is relatively well reproduced, with even a good location of the peaks in the profile. However, there is a difference in the intensity because you see that there are two scales in the same picture, and so we have used that to show that the shape is good, but the intensity provided by the simulation is about 2 times lower than the profile quantities obtained from experiments. So this is probably related to the point that simulations have been run in a shift-limited regime, while we are in the. It's not the case in the experiments. However, if you look at the estimate of the sol width, which is a critical parameter for the heat exhaust, then you see that the simulations here are not too bad, with only difference of 20% in the estimate between the experimental value and the numerical predictions. Either the simulation, either the step-off layer is estimated from the electronic pressure quantity here, or from the density. Okay. Then I will conclude this talk. So showing that we are addressing this research, so it's not finished. One of the main weakness of transport codes, which is how to predict, how to fix diffusion transverse diffusion coefficients in transport codes. So the model that we propose provide a self-evolution of kappa and epsilon to evaluate D and also characteristic time of turbulence that can be constructed by kappa over epsilons. So the simulation that we did in Emerald provide a very encouraging results. The nonlinear dependence of D allow one to extend the use of transport code to transients because the D is able to vary on time. And we can also, due to nonlinearity, when you take the divergence of kappa square over epsilon, then you can also consider some parts of the non-diffusive transport that will be related to advection. So we are convinced that such kind of model has a great potential of evolutions, but as we already discussed, for sure, there are strong assumptions even in the 2D fluid models, but also in the construction of the kappa epsilon model. And I would like to conclude by saying that we are over possibilities. So the idea that I would like that you keep in mind is the idea to construct a model based on over quantities to determine D. And over quantities can be kappa epsilon, or can be kappa and the characteristic time, kappa and omega, or entropy and over quantities, and so on. So the idea is how to model these transport coefficients using self-consistent model, calculating characteristic quantities of the flow. Thank you.
Is there any experimental implementation of for example, in the core, we know that there's a lot of transport that can happen of that.
And experiments, there is you can estimate from experiments the diffusion coefficients with respect to the density profile, for example, that you have, because you have only the measurements at one location, at the Lofisa midplane. And so from this quantity, you can have an estimate of the diffusion coefficients. And you have the scaling law, that you have an estimate of the variations of D with respect to plasma quantities. But
how is this week?
The result that we have, you mean? No, sorry. Yeah. So there is no evidence to my knowledge, there is no evidence that there is experimental results showing the connection between D and kappa epsilon. Two questions. So, yeah.
When you show the size of the lambda Q between west,
yeah,
that one is measured in air mode plasma.
It's L mode, yeah.
Okay. And so when you show that the radial profile of the density, and you show a nice agreement near stable layer region, but there's some discrepancy in the.
And which profile you mean here?
Yeah, that one.
Yeah.
So that's the reason was that your model not properly explain like the block dynamics in the bar.
Yeah. Yeah, it could be. Yeah. would be related to physical phenomena that we don't have in the model to explain these disturbances. The point that we observe is that we have not a sufficient spreading of D in the far soul, so respect even to turbulence fluid models. Yeah, but for the moment we have no idea to correct that.
My question is, I think within the thermoplasma, there's a certain region still Lister or nil Lister are still more important than yeah.
Yeah.
So how do you
cannot? we for the moment we don't take into account such kind of physics in the model. Yeah. For sure.
So 2 comments on the
Yeah.
questions. On Norman's question, I think the right answer is that the diffusive model is crap. I mean, the soul transport is strongly underneath. That's the blob story. Ask your former MIT buddies for infinite, particularly the Lombard, for particular infinite detail. On his question, in H mode, the transport is neoclassical, and you have basically no turbulence except in certain bizarre regimes, which is the point I'm driving at.
Mm-hmm.
But that brings me to my question, which is, if you're going to go down this road, which despite its limitations, I'll agree has some merits, it's certainly better than some of these full codes. I won't name the relevant 3-letter acronyms, you all know what they are. Why don't you make a package of simulating building a K-epsilon for the pedestal and the soul together, since these two are clearly strongly coupled?
Mm-hmm.
And again, to pound away on this point, any regime of practical interest is going to be something like an H mode with a turbulent pedestal, whether it be grassy elms or my D3D friends' white pedestal QH mode or I mode, as we were hearing about the other day, some conditions like that. So you're going to have spillover of the pedestal turbulence into the soul, which is actually good. Okay, and that would make, I think, a more interesting kind of structure.
Yeah, it's a good idea. Yes, the next simulations.
You would have to overcome, of course, the penetration of the spreading through the barrier, which is the central question in that. Which, I mean, there are now experiments going after that in many places. Since West doesn't have an H mode, West is behind the curve on that. Forgive me. But but I mean, other people will figure that out. So I think a tool of that sort, extending what you're doing, would be much more interesting.
Yeah, thank you for the suggestions. Yeah, thank you.
Curious to know what in the output of the simulations was the ratio of the convectivity.
But it's what I showed on the 3D simulations here. Here you can have an estimate of the ratio between the turbulent flux and the mean flux.
Yeah. I can't see the scale, but so it's the same order of magnitude.
Yeah, same order of magnitude. Thank you.
Yeah, no, that I know that. But I mean,